was right. This is a workshop. That's why you can interrupt me. I actually encourage you to ask questions right away. Don't hesitate. If you see something does not go the direction you expect, then stop me right there. I have a written plan beside me, so even if you stop me, I will always be able to get back to the snapshot and continue from the latest checkpoint. There is nothing bad about it. I encourage questions. I came here to talk. So the best benefit we could have and the best use we could make out of this conversation is by having a conversation, not a monologue of mine.
Actually, we have one participant that wants to talk to us right now, so maybe we can start with...
Yeah, please.
Yeah. Hello, Yuri. Yuri, you need to unmute yourself.
Keep silent.
Yeah.
All right, that could be a mistake. Yuri, if you are talking, then you are muted. Then please unmute yourself. Other than that, I'd like to add a few things. First of all, I'm a human being, and the entire thing I'm going to present is not LLM-generated fake. There is nothing from ChatGPT, believe me or not. I think nowadays natural intelligence seems to be sidelined a bit in favor of artificial one. But I take the old school approach in this regard. I think engineering is an old school thing. I actually tried to ask ChatGPT a few questions on the topics we're going to talk about, and the answers were simply wrong. So LLM is not good in the questions we're going to touch. Then, of course, I know a thing or two about computers since I'm doing it for more than a decade already. And which is more important, I have some background theory too. And everything I teach comes from my engineering experience. I have been applying these techniques really to solve production issues live till these days, till nearly a week ago. So this is kind of a live experience, and it was applied to live systems, especially those which are under heavy load. They run in production, they're heavily loaded, and yet I was able to trace them and to heal them without stopping them, without interrupting them by applying these techniques. So yeah, it's a cutting edge of Linux, definitely. I'm going to show you the best what modern Linux offers you. I'm also going to show you, of course, the old-fashioned ways, how you could do that like 10 years ago. And then we will compare what's better. I strongly believe in a high-quality education, affordable for everyone, and that's why I'm here on this talk. I hope that this conversation will later be published and populated to extend as much as possible. You can find me on Telegram. That's pretty much the only social network I'm available at. I don't have accounts on other social networks. Here's my, nickname. If you think that you need to ask a question or whatever else, I'm always open for a fruitful conversation. And just approach me there. Hopefully we have Telegram too. Well, yeah, then let's roll. To set ourselves comfortable and gradually approach core of the conversation, I suggest we start from a historical preface. I'll start a large step. I will conduct a large step historical overview. I don't want to go into details too much because this is not the primary point of the whole thing. And because of that, many important facts are ignored on purpose. We just don't have time to account for every detail there. So I define prehistoric terms, which is a funny term here, prehistoric. I define it as like everything that was or used to be before async await stuff. I hope that everybody in the call is familiar with async await, used it at least once. It's a cool feature, made our life so much better. So everything that was before that is a prehistoric in my eyes. I'll show you a paper, a legendary one, because it was born in academia as always. I have a link here. I have actually a lot of links today. This is a paper by Philip Wadler, a famous guy from the University of Glasgow. His contribution to functional programming and modern tools we have in functional programming is enormous. In particular, he wrote in 33 years ago, at the year 1992, when I was born, that guy wrote this paper with quite provocative title, The Essence of the Functional Programming, the essence, right? It sounds like a bit categorical. And that was a very influential paper. That was a turning point. Because he used the concept of a monad. If you don't know what it is, or you hear this term first time, then that's fine. Don't be nervous. You don't need to know. Here is how it's spelled, MONADS. This is a high-level mathematical concept that was born in the modern mathematics like less than 80 years ago. And all of a sudden, this guy showed to the scientific society at that time how this high-level concept of mathematics might be useful for describing many practical, I insist on practical engineering problems. He starts from quite complicated, even philosophical to a certain extent questions like, shall I be pure or impure, which is related to functional programming, which is accounting for immutability. But then sooner or later, he arrives to a concept of a monad. And then the most interesting part happens. I'll guide you through the structure of the paper without going into details. I'll just show you how a guy at that time could argue that this is the good approach. So he took a few problems known in the industry, well recognized in the industry, that were challenging both for science people and for engineers. So he took a middle ground between two. The very first problem was interpretation, of course, building interpreters like Python, like JS, like whatever else. In academia, there is a common agreement that if you build an interpreter, you build one for a lambda calculus. So he built one for a lambda calculus. If you don't know what lambda calculus is, you don't need to. This paper is not about this stuff. I'm just being a bit, I go into details such that you have a bit deeper feeling and understanding of what's going on. But the idea was to build an interpreter. And then he starts from what is monad, blah, blah, blah. We can skip it because we don't need this section right now. And then he starts to building stuff using his idea of the monad. He starts from the standard, simple, the most simple interpreter you can imagine. Well, building simple interpreters is not that surprising. You can do that easily with many other concepts, so that's not entirely convincing. And then he takes one step further. He adds error messages to it by using the same abstraction without changing the definition. That's important. He did not change the definition of the monad. He simply changed the definition of the task, which will be solved by means of the monad. And then he claims that this is not enough too. You will probably need more contextual errors. You want positions, you want which row and column, violating some, let's say, syntax rules or whatever. So he added a context in the monad. Then he added an arbitrary generic state. This is where it's starting to get, like a real world tool, like a generic real world tool that can grasp many problems. So now it's a stateful computation, yet pure in completely residing within the functional paradigm, and you can execute arbitrary stateful computation within it, including recursive ones. Recursion is known to be complicated, but you can do that. Turns out you can. And that's not the end of the story. He continues, he pushes forward. Then he accounts for the output, talking to external devices, talking to your console, file system, whatever, networking. All of that could be embedded into monad by using the same definition. We still haven't changed it, and we will not change it during the whole paper. Till the end of it, the definition stays. And then he says, well, that's not enough. Let's take another problem. How about modeling a non-deterministic choice? And he builds a stuff that models an abstraction that models non-deterministic choices by leveraging the same abstraction. And then he says, well, that's not enough because our modern compilers and model execution models, they have stack. They have ability to move forward and backward down the stack traces. And he questions himself whether he can build that using the monad, and it turned out that he can. Not just a stateful computation, but a stateful computation which allows you to trace back and forth by traversing the state. He can do that. Once again, we're talking about the lambda calculus interpreter, and this point it gets pretty sophisticated. And this point it gets like it's a real world interpreter. When you have a backwards state and you can trace back and forth, that's practically a programming language. So it only few pages of scientific text took him to get to this point. And at this point, it's already surprising. That's not what you would expect from a simple mathematical abstraction that emerged 8 years ago. So, but by this stage, this is already pretty surprising, and his arguments are strikingly good. But he continues.
Can I interrupt you for a second?
Yeah, sure.
We have a question. Is this related to automata theory and grammars?
To a certain extent, yes, they are related, because since you can model state, you can model a stateful computation, and you can model stateful but no, it's not directly, it's stuff like that. The idea of monad came from the pure math and from the philosophy. So people who do not care about programming, do not care at all about programming, they invented that term. And for a long time, for like 30 or 40 years, that term was of their primary concern. And then a few computer scientists who were also good in math, they figured out how they might apply that idea to programming problems. That was the crucial, that was the revolution there, because they connected pure math with computer science. This happens rarely, actually, in science of computers. You don't see it often. That's why I'm showing you this paper, because this one really revolutionary one. Then he built a complete call by name interpreter, and this is quite an achievement. Well, by doing this, you can only applaud to the author, because that's the point when he practically solved that he can solve real-world great problems easily by having a monad. Easily. And the definition is not so hard. This is surprising. He did not give a complicated definition that has a lot of nuances, nothing like that. The definition is simple, and it can fit in half of a page. Half of a page, that's it. That's surprising. Then we can skip this part. Monad lost, it's a bit of math. We don't care about it because we're not mathematicians. And then the most important part for us. This is where async await started to emerge. This is the prehistoric phase of async await, continuing monads. He says, wait, that's still not enough. The whole thing is not about building interpreters, even despite the fact that you can build a very complicated one. It's not about that. You can push it even one step further. You can model continuation passing style kind of software with monads. At that time, by continuation passing style, they meant what we now mean by saying by addressing callbacks. So when you write something like set timeout in JavaScript and you pass a callback inside your set timeout, you actually, from their perspective, you are doing continuation passing style programming because you pass a continuation, a callback. So at that time, at the year 1992, 33 years ago, they did not use term callback, they used term continuation. There is no difference between two. They are semantically equal. It's just a different name for the same thing. And this is where async await works. Because
now we have another question.
Please. No, don't be sorry. I like questions.
Okay. Backward state is similar to back propagation used
exactly. It is back propagation. Yes, it is back propagation. At that term, back propagation as a scientific term did not exist. All right, they called it a backward state. But this is the essence of back propagation. Yes, that's the data structure named stack that gives you a possibility or gives you an option to travel back and forth by selecting a current stack trace where you are. If you have been doing debugging sessions all the time, when you stop upon your breakpoint, you see a stack trace of the currently paused thread, and you can move one level, two level, n level down in the stack trace and basically inspect the state of the whole program and every local variable and what's not. This is what backpropagation is. Backpropagation is important because the whole class of computer science algorithms require backpropagation, in particular the field you mentioned, but there are many others. Without backpropagation, you can't solve many famous problems. For example, regular expressions cannot work. Many regular expressions cannot work without backpropagation. And many graph algorithms, many tree traversing algorithms cannot work. So backpropagation is important, and because of that, he decided to incorporate it into the paper. But this is the most crucial, what you see right now, because he says that you can take a callback style and map it without losing generality, without loss of generality. You can map it to his idea, to the framework of a monad. And that was important, right? At this state, I think we can finish with this paper because we are no longer interested in the end. But this was influential, believe me. So many people who are good in math and who are open-minded researchers, they were inspired by it, right? They read that paper carefully. It was quoted many times, and I can tell you that now, 32 years past that time, we are in a good position to judge whether he was right or wrong, and he was absolutely right. He was strikingly right, like a prophet, because he ends his paper with a bunch of conclusions about the future, and he makes actually quite strong predictions about what future will look like. And every letter written in this paper became true, became implemented, and became massively adopted by these days. A good example of that would be LinkU in C#. Even despite that you don't know that LinkU implements all of that, LinkU actually is a monad, and actually was kind of, you can trace the path from LinkU to this paper. And there are many other things. I'm going to talk about them, async await included. As you can guess, probably at this time, async await eventually will be born by this idea. So this paper was quite influential and revolutionary. And then for 15 years, nothing too important, I guess, was happening. People were discussing this idea, trying to implement it. The Haskell runtime and Haskell programming language was the primary one who took that path, who took it seriously. People played, mostly academia people, played with this idea, but they never reached to engineering system. They never made it into production, all right? So it was like an academia toy thing, but everybody understood a great potential behind it. They just don't have enough capacity to implement it. So it took 15 years. This period of silence durated for 15 years or something like that. And 15 years from that, three gentlemen, Don Syme, Thomas Petrishik, and Dmitry Lomov, decided to implement that in F#. I'll show you another paper. Let me do that, because I think sharing this paper and sharing the originals is a good thing. It gives you a right understanding of what's actually going on. So these are the Microsoft guys, right? And they were working upon F# stuff. At that time, actually, many considered F# to be a toy in practical language. Like nowadays, at this time, many think of F*. If you haven't heard such language, if you did not, then you can Google it. F* is another language maintained by Microsoft, and many think of him as a toy language right now. At that time, the industry stayed under belief that F# was not rich enough, at least not for tough enterprise, not for tough projects. And well, I think they were right, because at that time, the language did not have a lot of feature you probably want your language to have and to offer you. In particular, poor support for asynchrony and asynchronous computations. So these three guys decided to solve this problem, the asynchronicity problem. Forgive me my spelling. And they started once again from the theory, because they are good in engineering, and every good engineer starts from theory, from theoretical understanding of what's the problem and how it potentially can be solved. And they actually explicitly refer the idea of a monad. I don't remember where exactly, but a lot, you see, I'm doing Control F on monad, and it occurs a lot in many different contexts. So I think this is the most important to cite. Asynchronous computations form a monad. Yeah, this is exactly the monad that was described 15 years ago relative to this paper, and can be a result from another asynchronous computation using this syntax. This is how they syntactically wanted to present it in F#. And then they say that you can return a result, blah, 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 well, obvious things. And then they give you an example, a simple code snippet that will compile and run till these days on a modern F#. This is how it should be written. This is a correct, appropriate usage of it, where you, in an asynchronous fashion, you get a web page on google.com, and then you count the length of characters returned. So it's a silly example, but nonetheless fully practical. And note how async is being used. There is no await yet, right? await statement was not yet invented, let's say like that. Instead of await, they use exclamation mark. Well, that's kind of syntax they think fits better the F# paradigm, because they were inspired by Haskell, and Haskell does a lot of this stuff. Haskell does not like wordy, how you call it, keywords. So they were inspired by Haskell, and they decided not to have an await expression, but simply do this in such a way. So then they made it part of the compiler. They made it part of the standard library. Here is the GitHub. Here is the definition. It's a generic definition. So this generic definition exactly follows what they have written. Well, of course, it evolved over time. So at this moment, it's a bit more complicated than at the beginning. More than 15 years has passed till that moment. But nonetheless, generally, at the structurally, at the bare bones, they share the same idea. This is the very same thing. A monad, a continuation passing style monad that was described in the year 1992. And this is the standard library of F#. All right, this is part of the F# and part of the ecosystem. And of course, such an innovation impacted C# significantly, because both teams were interacting in the Microsoft directly, actually, especially the gentleman named Don Syme, whom I already mentioned. He's the author of the paper, one of the three. So they talked a lot about C#, about F#, about the evolution behind there, and C# team loved how it worked. They loved the async package, and they decided to push it even forward to the next step of evolution. So they made it part of the syntax and a compiler. So at that time, they were considering rebuilding new compiler or building a new one. I don't remember the name for it, probably Roslan. So it was appropriate moment to change or to introduce new syntax. They did. They introduced await keyword, not only async but also await.
We have sorry, we again have a question.
Yeah, sure.
Haskell, yeah, you can see this. Haskell is used in Linux commands in Bash, or am I mistaken?
No, Haskell is not used. Haskell is a general purpose programming language. It's a functional programming language like F#. You can write your applications here, your web server, whatever. And Haskell started as an academia project, and now people do production in Haskell. Well, people who love functional programming. But at that time, at the year 1992, of course, Haskell was an academia research project. And so whenever you come with a bright idea and you think that it has a bright future, Haskell was a good place when you can talk with the maintainers and convince them to give it a try and to implement it together with support of the community. Actually, it is true till these days. Whenever you come with a brilliant idea on functional programming, on how mathematics can contribute into software engineering, you typically start from Haskell, because it has a community of strong mathematicians, and they're also good at coding. They build a great compiler called Glasgow Haskell compiler. Glasgow stands for a city located in United Kingdom, of course. That compiler is great in terms of optimization it can perform. It can perform very non-standard optimization that are not done, for example, by GCC, C++ compilers, C, Lang, etc., because it is driven by different principles, which are not fundamental to C++ or C or whatever. So this is an interesting topic, but I'm not gonna go there.
Can I ask another question?
Yep.
Can you maybe very briefly explain what a modant is? Because I feel that it is the key for all the discussion done so far. I know that it's a mathematical concept, but if you can give us a little bit of programming intro, it would be great. So what is monad?
I probably will postpone this question till the end of the conversation. In my
Okay.
past, I tried already like 5 or 6 times giving an easy explanation of what monad is, and it took me like half an hour. I don't want to do that like right now because it will sideline us from the main course of the conversation. But the question is great. I will definitely try to answer it at the end of this talk. Uh, well, okay. Back to where we were. So C# staff, C# team, they decided to implement async await. That was a brilliant decision. I like it. I personally used async await for quite intensively at the time when it was invented, and I loved it at the time. It made my life pretty much simple and life of every programming software engineer on the planet, at least who does a high level stuff, because pretty soon that feature was copy pasted to many other programming languages. Now you can find it in so many places. I will not list all of them. You can go to Wikipedia and ask how many languages do implement this paradigm. A lot. All right, and a lot more. They plan to land this feature in the nearest future. So eventually that will become a global standard. That's pretty obvious by now. So they basically changed how the entire planet, the high level programming industry approaches a certain kind of problems, right? Well, that sounds like an achievement to me, hopefully to you too. And then a bad thing happened. And then because this feature was introduced, people started to write documentation on it, on how to use it, right? And I'm giving you a modern example. This is what Microsoft says about async and await, and this is how it kind of instructs you to choose one. And it gives you a quite tiny table, and it kind of asks you, are you IO bound or CPU bound? And depending upon choice, it gives you two different suggestions, all right? And this is a bad thing. Despite that they contributed a lot of good things, this is a bad thing, because if you have no clue what are you doing and how it works, and to have that understanding, you have to start from the hardware level. Otherwise, good luck. Your understanding will be incomplete, and you won't be able to grasp the very essence of the whole thing. So if you can't understand that at the hardware level, which they do not describe, then you're doomed. This section of documentation will make it even worse. You won't be able to make a reasonable choice. You won't be able to reasonably understand how to measure your solution, etc., etc. So this is not an engineering. This is becoming a religion. But for those who has this knowledge already, this section is useless, because you already know that, and actually this table does not give you anything special. There are many examples of such problems, and this is the turning point in the history of the question, because many young programmers, they go to the documentation, they don't read kind of fundamental books or fundamental papers. I don't think that people often read the source code, right? They tend to read documentation, or nowadays they tend to read what ChatGPT says about documentation, so it's even worse. And a lot of details are simply not there. So your decision-making process becomes corrupt, all right? It's incomplete. And you stop to be an engineer, and you start to be a coder. This is why I'm here. I want kind of to fill the gap.
And also we have a
I
question,
want to...
quick
Sure.
question. We have a few comments, but I think we need to focus on
We can
questions.
make a pause actually right now and go through the comments, because we kind of checkpointed. That was...
Okay, let's do this. So you can actually read this. You have this from Alexander. Do you have some of this concept in modern Java? Do you know, or possible in third-party libraries if applicable?
Yeah, we have everything in Java. It's just I'm not sure that you have a compiler support for that in Java. No, I'm not aware of that, and I'm not actually a Java guy. I might be mistaken. But last time I saw Java, I have never seen nothing like that. But you definitely have all of that and even more in Scala. So Scala was the platform that implemented all of that. And Scala, by the way, was much influenced by Haskell. Many Scala features are kind of direct projections of these ideas taken from Haskell and from academia to their runtime. So you can do that in Scala for sure, and I have been doing that in Scala myself. That's for sure. You can probably also do that in Java, but that's not going to be convenient. And I would recommend not to do that, because you will fight with your runtime. Other questions?
No, we have a few more comments. I think, yeah, consider this topic.
Yep. Just let me scan through the comments. Pass. Well, I did not get the idea. The main idea of functional programming is pass the mass notarian into programming code. Well, I'm not sure what you mean by that. Sorry. If you could expand your reasoning, it would be nice. Yeah, all right. We don't have more questions for now. So let me continue then. Well, we have to get a hard code now. We have to start coding something. Back to this documentation, since I used it as an example. Well, it kind of mostly correctly communicates that there are two different classes of, let's say, workloads. That's how I call it. First is IO bound, the second is CPU bound. Actually, there are more, you will see that, but this is a good starting point. Let's start from the CPU bound and try to write a code and try to do something CPU bound and see how we can analyze that and how we can trace performance of that. So first of all, again, I'll have to share with you a good material. Sorry. I'll have to do this. I have some good materials prepared. So CPU is a piece of hardware, right? When we're talking about CPU and how to utilize that, if you think you can do that without understanding how CPU works, at least at the general level, general enough, then no, you're fooling yourself. You can't possibly do that. That's a common misbelief of young programmers nowadays, that you can't do that without understanding how hardware works because you have high-level programming languages. Yes, you do have high-level programming languages, but this does not make you free. This does not set you free from understanding how the hardware works, because otherwise you will use these programming languages and write a bad code that is purely executed on the hardware. And I actually will write a purely executable code that will be of awful performance, and then we will fix it. But the important part here is that when you jump to the key concept, and I like the naming, I like the phrasing here, key concept, very brief and straight to the point. It starts from the cache line. The very thing you see, the cache line, that's number one, right? Nothing else is important. So when you talk about CPU bound and being CPU efficient, the number one thing you should think about is cache, CPU cache. I'm currently executing a Linux command that gives me a size of the cache line. It says 64 bytes, all right? The other way to do it on a modern Linux, which has a sys fake subsystem, is by issuing this command, where index 0, 1, 2, 3 stays for different hierarchies of the cache, because cache is multidimensional nowadays, and there are multiple levels of that. This paper that I'm mentioning here, it makes pretty good point. It says that cache line or cache blocks are the unit of data transfer between main memory and cache. So what is the main memory? This is your RAM. This is the gigabytes of memory you typically have nowadays, like 16 gigabytes. My laptop has 32. A CPU core does not have access to that, right? A CPU core does not have 32 gigabytes of RAM hardwired directly on it physically. No, it doesn't work like that. They're connected via bus and etc., etc., etc. The memory CPU has and actually kind of possesses is cache. That's the only memory it has. That's why this distinction, main memory and cache, and they kind of term here. You have to treat them like a terms. They have a fixed size, which has been 64 bytes for many years on x86, x64 platforms. Well, not actually on these platforms. The other have 64 bytes rule too. This rule sometimes is violated. It's not like 100% of the cases, but most of the time this is true. So you have a cache line of size 64 bytes. This is important to memorize. If in your career you're going to write CPU intensive code, this knowledge might be crucial. The understanding that you have only 64 bytes of a cache line, all right? It sounds weird, but it is what it is. Low-level code requires you to understand these details. You can't proceed without it. You can always check on your system by issuing these commands, but very unlikely you will get something else except 64 these days. And now, the most interesting bit, which will probably surprise half of the audience, that whenever you're accessing a single, this is just a simple example, you're accessing a single uncached 32-bit integer. 32 bits means it takes 4 bytes. It actually entails loading another 60 adjuncted bytes for free, because the entire cache line will be filled by the adjacent memory, and that's called the prefetching. That's how hardware does, and you can't turn it off. This is an unconditional mechanism that makes your CPU performing well. Whenever you access a memory location A, it will actually prefetch next 64 bytes from that point, even if you are not interested in them. Why? Because probably your next instruction or a couple next instructions will load the neighbor memory, right? Because typically,
Serhii, can you please zoom a little bit the text
yeah,
participants ask
sorry,
that.
I will do it page fit.
Thank you very much.
So this is called the prefetching. This is an optimization mechanism that really wired in hardware. This is not a software level. This is a hardware level. Whenever you talk to a memory location A, you get an entire cache line, which is 64 bytes upfront, right, from that position. That practically means that if I'm reading integer, let's say I have an array of integers, 32 bits integers, and I'm reading the very first one, and then I get 16 of them simultaneously by a single load instruction, because I will get entire cache line, and cache line is 64 bytes long, and that means I can have 16 integers within it, right? I can get 65th, I can get 17th integer, because it will not fit 64 bytes, and I will have to leverage and consume another cache line. And that practically means that if I pay something that is implied by talking to main memory, if I pay something to access the first integer in my example, then accessing second, third, fourth, and up to 15th is for free, because I'm going to talk to my cache, my local cache. I'm not going to talk to my main memory. So let me demonstrate that. That might sound kind of, impressive if you have never heard that. Just give me an example. I will copy paste my, sorry, something wrong with my second monitor. I can't copy paste. Why? It's a live session. We always have issues like that. Okay, let me try to fix it. Yeah, let me try what's happening with my system. Does not react on what's happening. Let me try to rejoin. Can I? Will it break if I rejoin?
No, that will be totally fine. So you can rejoin.
Yeah, let me rejoin for that.
Yeah, guys, please stay here. We just need like a few seconds, I think, up to 1 minute to reconnect, and everything will be fine. And yeah, I see the new question. When Serhii is back, I'll let him know about this question. Don't worry, we're not stopping the event. We will be here. And guys, just a quick comment, because I've noticed that some of you maybe haven't noticed that when you write in a chat, you have the option to to who you are going to write. So please choose option to everyone, because I can see everything in the chat. But that would be very nice if other participants can see all of your questions in the chat as well. So if you write something, I mean, if you want to write something personal to us, that's totally fine to use the host and panelist option. But basically, if you have a question, just use the option to everyone. So everyone will see a question. Maybe somebody will help you to answer them, actually. Yeah, because I see a lot of comments, people just answering each other. So yeah, thank you. Since we're waiting, you're very welcome, yeah, to communicate with each other in the chat. But Serhii seems like is back with us.
Yeah, that was tough, but this always happens. Whenever I have had live sessions for many years right now, everything. Sometimes something is broken all the time. All right, I think we're back, so let's code something.
Actually, yeah, and with during this time we already received some of new questions. Can I read them out?
Yeah, sure.
So the one question is, but you can omit this cache with volatile
No. Well, yeah, you can to a certain extent, but that will not omit cache. That means that you will have exclusive access to the cache line, and your hardware cannot omit cache by definition. All right, your hardware is wired, your CPU is wired in such the way that you cannot load the memory directly from the main memory, because this is physically impossible. You can talk to main memory only through the data bus. All right, that's the only way you can do it. That's by definition. This is how the physics works. Nonetheless, what you can do is you can say that, all right, this piece of memory or whatever this address is exclusively mine, and you will ask your compiler or your runtime to execute a much worse and much less performant code, because whenever you have a multi-core infrastructure, you have multiple cores, many CPUs, you have probably 12 or 20 of them, depending upon your architecture. And that means when your core A accesses that exclusive cache line, then the rest 19th or 11th CPU cores must wipe and must invalidate their cache line. And invalidating cache line is costly, right? This is extra job you got to perform. So you will actually run slower and you will run worse. Exclusive access is how to say, you pay for it. It doesn't come for free. All right, so this is the C code, right? We're hardcore guys. Why don't we write a bit of C? Later down the road, I will show you high-level examples. Don't be afraid. This is not going to be a C session all the time, but demonstrating CPU stuff is best done in terms of C. I'm having a pretty simple code here. The nitty-gritty details are here. I'm defining a struct, and there is a very special attribute that is commented out. Because this commented out, actually this version of the code will run smoothly, fastly, and perfectly fine. But if I uncomment it out, And note how it has 64 bytes in it. Now you should understand why. If I uncomment it out, then things will go wrong. Terribly wrong, and we will have small performance. So actually what this code does is a very stupid thing. It first dumps the size of the structure and the size of int. Int will always gonna be 4 bytes on my platform, but the size of the struct I defined depends upon whether this attribute is commented or uncommented. You will see that. Then it allocates a large enough array, a continuous segment of memory of these dummy structs. I even don't care to fill them with non-zero values or whatever. I don't really care what's going to be there. This is not about their content. Has no importance here. I call the variable we do not care because we do not care really, and then we do a simple summing operation. It could be whatever. It could be bitwise operations, any arithmetic, whatever you like, whatever CPU is good at, any instruction would work. Once again, this is not important.
Also a question. Does the cache works in the same way in GPUs and TPUs?
Well, almost, yeah. No, the cache lines are shared in a different way. The protocol is different, but yeah, they also have that, of course. You have to, well, there is a fundamental reason. This question lacks a fundamental understanding. There are fundamental reasons, right, that having one single, let's call it uniform type of the memory is not viable. You can't have one single uniform type of memory by definition. Why? Well, physics answers the questions. Obviously, we have a speed of light, all right? And no single can propagate faster than the speed of light. Well, according to the modern physics, at least, and according to the electrical engineering. That's the very first factor every textbook on electrical engineering will feed into your brain, into your mind. You can do faster than speed of light. And thus, every storage technology, this is important, can only reach a finite amount of data within a desired access latency. Access latency is important. If you don't have caches, if you omit them at the hardware level, then you sacrificing access latency. By access latency, we mean talking to main memory, because you have to comply with the protocol. You have to go to the memory bus. You have to ask for a certain memory location, and then you have to wait for memory bus to actually get that memory location for you and come back to you. All right, and this is waiting. You pay for that, and it does not work that fast because you have 20 CPUs all together, and all of them simultaneously in parallel request memory access. Your data bus will not handle all of them simultaneously. They will kind of include them in a more or less serialized execution, which means that many of them will wait. All right. So talking to main memory is a problem. And since we are not willing to sacrifice access latency, we have to avoid uniform type of memory, and we have to invent caches. The question is how many? Do we need one cache, or is that going to be sufficient? Well, Intel and AMD answers that questions. They say no, you have at least it's better to have at least 3 levels of the cache: level 0, level 1, level 3. So typical architecture right now, these days have 3 levels of cache, okay? And it's gonna be even more complicated probably, because Intel has already announced that they're working on a new cache protocol that will kind of incorporate more complicated caching strategy. Yes, I'm oversimplifying things right now. The manual upon how Intel works takes like more than 800 pages, of course, and significant portion of that is allocated for cache operations and stuff like that. So cache is complicated at hardware level. Don't think that this is quite simple, that this is a simple cache like a dictionary, which you can imagine when we have a key and you kind of do if key present in the dictionary, then give me the value. No, it's not. It's much more complicated than that. And cache evaluation protocols and cache coherency, cache consistency protocols are extremely complicated. All right. We have this variable we do not care. So this section simply makes CPU hot. We kind of do a dummy job. We don't care about result. We care about job being done, because we want to waste some CPU cycles. We won't put CPU under the load, because this is what we're going to measure, right? We need an artificial load. It could be whatever. And then I print the result. Yep.
We have the
Question?
questions. Yes.
Yeah, that's
So
perfect. Nice.
I hope I'll just read all of this correctly. It seems DRAM drum, I think, controller introduces latency, but in much slower than static memory built in CPU cores. Sorry, I don't know if I read it correctly.
Well, no, caches are much faster. You will see it right now, actually. I will demonstrate you that reading from caches is much faster nowadays than reading from the memory bus and stuff. And be aware that my laptop is quite modern. I have a modern Intel chip, and I have a modern hardware, and I have a hybrid configuration, and I have all of that activated in BIOS. So I'm and my laptop is optimized right now for top performance. And despite all that facts, you will see the significant difference right now. This is even more true for less optimized systems, for commodity hardware, let's say.
Oh,
All
we
right,
have
so we finally,
question.
yeah,
Sorry.
sure.
If you're iterating an array of 16 integers one by one, and cache will be filled with first item plus all other items, thanks to fetching, does the CPU understand that it can take all of the array items from cache?
Yes, that's the point. Of course, it will. Not only, once again, CPU does not have to understand that there is a protocol wired in the hardware. When you execute a load instruction, it necessarily, unconditionally goes through the caches, necessarily and unconditionally. And you can, by the way, calculate cache misses. I will show you how. You can calculate how many cache misses have you had during the execution. And by calculating that, you will figure out how efficient your cache is. All right, that's the primary technique there, and of course it will. That's the whole point. That's how optimization works. You will not waste your cycles on accessing the other 15 integers. You will not talk to memory bus. You will get them right away. That's the whole point of the optimization. You got it right. My congratulations. So yeah, that's the software we have. This is a C code, so we have to compile it. I will compile it with the most possible optimizations minus all three. We called it CPU like this, and we say that we need the file that will, the executable that will be called CPU. I hope that's the right command. Yeah, probably it is. Now at the TMP, we have a CPU and we can run it. Yeah, and it runs fine. So it compiled. Note that the size of an int, a structure, an artificial structure as defined is 4 bytes, and the size of int is 4 bytes. That's the good point, all right? That's how it's supposed to be. Now we are going to analyze it. We're going to analyze it. How do we do that? We do that by using perf, all right? Perf says use that this is a performance analysis tool for Linux, all right? Not much, but this is one of the oldest tools there, and this is part of the standard tool stack. Every core Linux guy knows how it works, and if you kind of if you work with Linux on a daily basis, then probably learning this tool is a good idea. Under the hood, perf works under the, I think, ptrace. Ptrace is a system call. It's part of the system call set that are given you to Linux. The ptrace system call provides a means by which one process, the tracer, may observe and control the execution of another processor, the tracer, and examine and change the tracer memory and registers, right? So that is how you hack into another process, which means that perf will execute a ptrace on the process we will not start, and by executing that, perf will be able to analyze what has been happening, the state of the CPU, how many different low-level operation it performed, count them, and then report. All right, this is how it works. The drawback of this is calling a syscall named ptrace, because obviously it makes things much more slower, and this is explicitly mentioned here. It is primarily used to implement breakpoint debugging and system calls tracing. All right, obviously debuggers are not fast. They make things slower, right? Because they kind of interfere with executing program, and they have to inject additional instructions that otherwise would not get executed. So we pay for that, and we have to keep that in mind when we are doing ptrace.
We have another question.
Yep.
How to understand whether sequential where parallel data access in CPU cache area SSD line in high load system with many CPU cores and their cache shared RAM, etc.
I'll show you. This is a good question. It can be answered in many ways. One of the ways that you have your source code that defines the access pattern. If you write a for loop that kind of sequentially traverses the array, then you're good, because array is a continuous memory, and you traverse it in one by one fashion, then hopefully cache is gonna be fine. If you do it randomly, or if you do a lot of random stuff, like for example, you're having a linked list and every next link could be located or allocated wherever in the memory, then you have to make potentially large jumps between every node, and that's going to be bad. So one answer to that is use right data structures, and that's probably the most important, and define your algorithms to be such that they do sequential access. That's going to work. But there are some cases when it's not possible. For example, graph traversal. Graphs by definition are sparse. You can't possibly make them continuous or too condensed. Then the data structure simply does not fit the requirement of being CPU friendly. Many data structures are CPU friendly, some are not. You have to accept it. Graphs are the prime, especially directed graphs, are the primary examples of that. Well, except that, there are also a lot of optimizations done actually by compiler to make your imperfect code much better CPU-wise. You could do that. And you can trace it live. Your question, how you can trace the pattern of how you can trace the pattern. Well, you can't trace the pattern, but you can count how many cache misses and cache hits you have had, and which level of cache. Even that can be traced. Yeah, you can even trace which memory locations you're querying live on a live system. But I doubt that will be helpful. Counting cache misses and cache hits might be very, very useful, and we will do this shortly. I'll show you that this is indeed the case, and this is helpful. So I'm running.
Sorry.
Yeah.
When optimizing cache operation on a virtual machine, are we constrained by the hardware hosting the virtual machine? Mainly the question is optimization is variable and you are getting a range instead of a value, like 15% improvement.
Well, it depends upon what virtual machine and what virtualization is used in place. For example, Linux has C groups for that, control groups, right? And how you call it, namespaces. There's the feature implemented in the kernel space. And it gives you much better virtualization and indeed much better access to the hardware. So it does make sense to do all that stuff. But there are, of course, many virtual machines that are kind of inefficient, and your optimization will not play that good, will not have that good impact on the virtual machines. But there is no general answer. You have to trace. You have to try and measure. That's what I'm teaching you. I'm giving you a set of tools that you can apply and reapply, whether on your local workstation or on your production. And I encourage you to do that. I've been doing that all the time, actually. I've been personally solving a lot of production incidents and production performance issues live by doing this kind of stuff. Well, not exactly using perf. Hopefully, we will get to eBPF today, but yeah, in this fashion. So it requires me a password. This is a good thing, and we see the numbers. That is what I told you. We see a lot of stuff, context switches, CPU migrations. We don't care. What is important here? I'm looking instructions per cycle. Yeah. So this matrix is important. Per one cycle of a CPU core that was involved in execution, and we see that almost an entire core was utilized. 0.0993 means that almost 100% of a single CPU was utilized. Then most of it, on every cycle, we executed on average 2 instructions. How that could be? Well, that's because Intel has a lot of optimizations. Well, I told you that I oversimplify things, and when you do really CPU when you try to when you write CPU friendly code, your hardware will actually optimize that further, and you can have up to 4 instructions per cycle on my architecture. So each cycle can execute 4 instructions. My example was not so friendly, so my hardware was able to execute almost 2 instructions per cycle, which is great. Each cycle CPU did perform 2 useful instructions. All right, this is perfect. And we are CPU intensive here, because every cycle does useful work. You can't wish for better. There is nothing to be wished for. This is a good, not a good, this is probably a best possible performance. We can also specify particular events when interested in instructions, cycles, and cache misses, I think. No, cache misses are not that. Cache miss. Let's delete that. Sorry. Instructions. Cycles. Yeah, that's right. So let's add cache misses. We have something like that. So this is the number of cache misses we had. You have to understand that this my architecture is very complicated. I have a hybrid CPU core. CPU core is good for high performance stuff. CPU Atom is good for power management and low power operations, and my Intel platform tries to adopt live, right, on the existing workload. It tries to choose the best strategy. So you have to account for that. But this is pretty good pattern. We are executing almost 1.5 instruction per cycle. This is a kind of good, all right? This is what says that you're utilizing your CPU in the not best, but quite good manner. Let's do it bad. Let's make it terribly bad. So all of I did, I uncommented a single argument, and it instructs GCC as a compiler to align this struct on 64 bits, 64-byte memory addresses, which means this structure will now be at least 64 bytes long, not 4 bytes long, but 64. I recall that previously, if I go back and execute it, now this structure is 4 bytes, right? But let's recompile it. Well, I think I did not save something. No changes. Maybe it should be not here, but it should be here. Let's see. Yeah, now we're good. You see the number 64. This is what I wanted. The number here is 64 now. So the size of the structure is now as long as the size of my cache line. Wow, that's going to be bad. Because of that, my cache lines are useless now. Because of that, now every time I access my data structure on the index 1, it is so long that it occupies an entire cache line. And it means that when I will try to access the neighbor, the adjacent data structure, on the next index, it will again go to main memory, because it can't read it from cache, because I broke the prefetching, because the prefetching is limited by 64 bytes. And you can see that easily if you do the same perf stat. You can even notice that it runs much longer. I did not change nothing, but it now runs almost 5 seconds or 4 seconds. 4 seconds. It runs 4 seconds. Come on. And you see that somehow instructions on my CPU Atom are dropped on less than 1 instruction per cycle, 0.77. For example, this CPU was not able to perform even a single useful instruction per cycle. Why not? Well, because it was involved in cache invalidation, and because it was waiting for memory bus. This is exactly the reason. And still, we utilized all the CPU. So CPU was busy, but was busy with nonsense. CPU was busy with talking to the main memory because cache was useless. That's a good example of that. It should be pretty clear that caches are important at this point. And you can break it by a single inappropriate attribute, all right? If we make it 512, then it's gonna be even worse, all right? There is no limit how bad you can make it. GCC will comply and will generate an awful code for you if you request it. So actually the book, the textbook I mentioned, it gives you another great example. It gives you a linked list example. Examples, std vector versus std list. So to my understanding, I'm not a C++ guy, but to my understanding, std list is a linked list under the hood, and the std vector is an array. And then they do roughly the same. They do what I did, but in their own fashion. And they also perform the same kind of analysis, and they get the same result because arrays are continuous segments of memory, and linked lists are not, because every next link can be placed arbitrarily in the memory. When you traverse a continuous array, your prefetching works fine. When you traverse a linked list, then no, you have to talk to memory bus on every next node to fetching every next node is costly, all right? And they get the same misperformance, right?
We have
This is due.
actually
Yeah,
a few more questions.
sure.
So I think these two comments, okay, I will maybe read them how they were written. So in what part we can rely on compiler optimization, and what time we should work with our code and profilers for addressing that software versus hardware bottlenecks problem. As far as I understand, the more you adapt your code for one hardware, the lesser it is portable.
Well, no, why? No, I don't think you're right. You have to pick a right data structure and avoid, silly attributes the way I did, all right? You have to keep in mind that prefetching is there and does a great job for you. That's the whole thing you have to do. The whole point of this demonstration is being CPU efficient nowadays, at these days. It's not that important because compilers are there for you. All you have to do is to leverage cache. And by when I say leverage cache, I really mean don't break the cache. Try not to break it because it already works. It's already there. So you have to, if you want to be CPU efficient, you have to solve every your problem with arrays, first of all, with low-level data structures that fit into the continuous segments. It's a good question. Why does .NET runtime and other many famous runtimes have clear distinctions on structs and classes, right? Value types and how you call them, referential types. Well, because value types are CPU friendly right now. You should be able to understand that they are friendly for cache prefetching because struct types are short in size. A Boolean is short in size, takes 1 byte. Int 32 is short in size, takes 4 bytes. Double is short in size, well, relatively. That's why they're structs, because they're good with prefetching. And by using structs when appropriate, you made your code CPU optimized. If you will use linked list, if you will gonna use linked list all over the place, or you will have crazy allocation patterns like I introduced right now, when you skip entirely a cache line by a simple mistake or misalignment, then you're done. Practically, to be CPU efficient, it means not to talk to main memory. That's it. That's the rule of thumb. There's really nothing to tell more about it. Just don't use, don't talk to main memory to extent possible. I hope that answers the question. Tell me yes or no. What other questions do we
So
have?
we have a question, but I think other participants already seems like answered. So what will actually happen if our data structure is bigger than CPU cache?
Then you will not get part of this data structure prefetched. If it's bigger than your cache line, then you will not get it prefetched, and you will issue another load memory another load memory instruction will be necessary that will talk to the database and will talk to the main memory. There is no surprise there. If you can't fit nothing in your cache line, you can't fit in your prefetching mechanism, then you have to repeatedly talk to the main memory, and that might be fine. I mean, don't be crazy about it. Just keep in mind that accessing main memory is costly. That's it. Don't be crazy about it. And that actually explains why the entire industry is so much heavily optimized for arrays, because arrays are continuous segments of memory, because prefetching was tuned and invented and configured to work with continuous memory segments. That's why linked list is not used mostly in the industry, except very, very special cases. And your compiler is heavily optimized for generating continuous, continuous like code. And you can use arrays all over the place if you want to, but then you pay for relocation for growing these arrays, right? It also doesn't come for free. There is a trade-off always. But CPU, but when you are able to kind of figure out where is your CPU intensive part of the application, typically it's a tiny bit of your application gonna be CPU intensive really. For example, in browsers, CPU intensive part is rendering. All the other stuff is not CPU intensive, but rendering, when you start to compute geometry, that part is CPU intensive. So you can kind of slice your CPU intensive subsystem or subflow, and then you can responsible, which means that all the other part of your system might not use this approach because it's not needed. That is the part of the part of the workflow. And I actually mentioned that in the title of the conversation, that this understanding of the core differences of different workflow leads to a better design. Because now, if you know that this program is CPU intensive, you will design it differently. I bet, at least I would hope so, that you will. All right, are we ready to move forward? All right, we have 7 minutes till the end of the conversation. I'm kind of half done. We had a lot of questions and I appreciated that. We can approach in 2 possible ways. Either I can stop right there and answer your questions, or we can make a, let's say, 10 minutes break and I will continue. And I will get to the end of the conversation and show you the IO stuff. It's all up to you guys. I don't know what works better. Or we can have an open conversation right now.
I can actually maybe help you to decide. We can, I don't know, your plans for today's evening. We basically can stay a little bit longer if you can do this. But yeah, so we can stay longer, like for, I don't know, 20 more minutes. We still have new question in the chat. So seems like our participants have a lot of questions. So maybe we can concentrate on them. Basically, can we focus more on the session and bring questions at the end? Some questions could be answering during session, I think. Or maybe, yeah, maybe you can go back to the live coding part and then we will cover as many questions as we have at the end. But maybe some questions will be unanswered,
Yeah,
so we will write
sure.
the answers in email, for example.
Yeah, then let me continue. I will try to do it really quickly.
Okay.
Let's pause questions for a while. You guys, you still post your questions in the thread, but they will be answered by.
Yeah, I
by the end
remember
of
where
the
we
conversation.
stopped, so which questions are unanswered, so we will be back to them when we
Cool.
can.
So we've been doing a lot of CPU stuff, and I already shared with you some ideas behind that. The next step is try to hit something that is not about CPU, either disk or network or something like that. I will do that really quickly. I have a comment for that. So DD is known to be a disk destroyer. Be careful with it. It can really destroy your disk. This is not a joke. It does a copying, like a copy instruction. If is in input file, it copies from dev0. OF is output file. And this is the block site, and this is how many blocks we are going to copy. For those who are not aware, /dev/0 and /dev/now are virtual devices. They do not exist physically. They're part of the kernel space and they're kind of simulated. They're virtual. Keep that in mind when you now see the results of this execution. So always instantly, we get an outcome, which means it was pretty fast. A crazy number of 10 gigabytes per second speed was calculated, but yet you see how low the instruction per cycle is. 0.27. So almost no useful cycles were performed during the execution. Almost no useful cycles. And you see that we spent 0 time in user second and most of the time in the kernel space. All right. So why so? Why CPU does not do useful stuff now? It used to perform always 2 instructions per cycle, almost 2. And now how much worse is it? More than 5 times, right? 10 times, almost 10 times worse than it used to be. Why? Well, because you don't do CPU, because you don't behave right from the CPU perspective. You're asking it to do a non-friendly operation, all right? Copying is not friendly. Why? Look, because you're copying from virtual devices which do not exist, you don't talk to hardware, all right? You talk to main memory, because this type kind of live in the main memory. This is a simple generator of the zeros, like endless stream of zeros, all right? Generating them is cheap. You don't need a lot of CPU. It basically amounts to a instant return 0 statement, all right? That's cheap. But then your data bus and the speed with which you can transfer the data becomes a limiting factor. So if you recall, the Microsoft documentation states that there is either IO bound or CPU bound, and that's a lie. That's how you get a wrong picture of the world you're living in, because you can also be memory bound. This is the example of being memory bound. We are right now our CPU does nothing because it has no incoming request, because we are saturating our data bus. It cannot deliver faster than 10 gigabytes of data per second. Come on, it's already too fast for it. It was not designed for that speed. Because of that, our CPU does nothing, actually. And we are memory bound in this case. You can be memory bound. You can be network bound, by the way. You can be disk bound. You can be bound by whatever resource or whatever device you have in your ecosystem that cooperates with you, that have a notion of a request and a response, and you kind of expect it to reply to your request. Then you can bound by that device and its throughput, because every device have its limitations. You have to be aware of that. So next step is to try to talk to something that does exist. I don't know, maybe to a disk, right? Or something like that. Because I'm trying to be fast here, I will skip a few fruitful examples that I have, but we don't have enough time. So this is a real device, SDA, a hard drive I have. And now we will copy from that device directly. So this command will actually talk to disk. And now you will get all the implications of that. Look. Well, it actually a bit better. Your cycles are a bit more useful right now. But still, see the difference. 1, 2, 3, how much? Less than 100 times? I can't calculate. More than 100 times slower? You can only pass a bit more than 100 megabytes, not gigabytes per second now, because my hard drive is slow. And now my CPU gets more requests. It's not bound by disk, definitely. It has more requests to process, and it starts to process these requests. It starts to do copying and starts to do a useful job related to copying the raw bytes it was given by the disk. This is important, the difference between the numbers. This is important to figure out what is the limiting speed of your drive. right? If you read the passport manuals, then you will see that your typical commodity HDD drive, hard drive, will give you speed roughly 350 megabytes per second at the top of performance. If you buy a really expensive one, it will promise you up to 700 megabytes, still not even a gigabyte per second, but you will never reach there. Good luck having 500. That's from my experience. So this is a reasonable number comparing to the expectations that they give us, and we are definitely not reaching the upper limit of it. So it's not saturated, and we are not bound pretty well. So we are good. And now we are not talking. Well, now we are talking not only to main memory, of course, but also to the disk. So now CPUs have to wait for the disk to answer. If there's going to be an SSD drive, then you will have a few gigabytes per second here, much faster. But still, your CPU going to be limited by what you have. Let's do Python. I promised you we will not we will do high-level stuff. So this is a joke copy. I'm asking for a bytes. I'm asking an external service, an external web server to give me a joke. A simple Python script, almost one-liner. I can run it like this, and I will get jokes, right? Important to understand that this web server lives somewhere there. I even don't know where. Which part of the planet it is, I don't know. But it's far away from me, which means my computer can do nothing about it. It can only issue a request and then wait for the reply, right? And while I'm waiting for the reply, there is not much I can do. I don't have useful job. That's kind of important. Let's see what's happening. Let's do an strace -m, and then we run the same command. Strace Python temp. Yeah, it should be like that. Sorry. So this is a number of system calls that are executed live by my application, by my Python application. You see mostly read statements here, right? Sometimes you see connect and mostly read statements. You can actually have a summary of that by issuing -m flag. Wow, maybe like this, no? Should be -m, why not? That was -c, sorry. -c stands for this summary. And then it counts the system calls that were issued. And you see that at the top, we have like 700 for these few seconds that I let my application to run. We had almost 1,000 of read calls. This is the system called read. And obviously, when you read something, you're issuing a request, and then you're waiting. You do nothing. What possibly useful job my CPU can do while I'm reading? Well, it can't. That's the point. It can't. This is entirely different workflow. There is no much CPU can do, and the very notion of cache prefetching does not apply here. There is nothing to prefetch, because what we are trying to read from even does not exist probably on this part of the planet. You have to travel over the ocean to get the right bytes. So the very idea of prefetching is useless here. The whole infrastructure Intel built for CPU optimization is useless here by definition, because this kind of the problem has a very different nature from the previous one. And why so? This is because my bytes have to travel through the sequence of routers. And what else can they do? This is how the world works. So all the optimizations we had so far and all the tips and tricks we discussed are useless here, and we have to start from scratch. And by starting from scratch, we are becoming an IO bound here, and we are learning a new paradigm, a completely new way of solving a completely new problem, which will imply a completely different technique to solve this problem. This is where I think await is eventually can come handy. But in order to understand it better, we can also do it like this. Let's try to do it in a different way. So I'm now measuring time by using user bin time executable, and that gives me a summary of what's happening inside. And I'm particularly interested in these voluntarily context switches and involuntarily context switches. All right. I also, it is interesting to notice how many time we're spending in user space and how much less we're spending in system time. The difference is significant here. We can also see that CPU is almost not used, 30%. There is no job to do, simply. But the amount of context switches for 3 seconds is kind of surprising. I let this application to run only for 3 seconds. Why did it do so many context switches? Especially, what's the difference between the voluntarily context switches and involuntarily context switches? Why so? And let me try to find that for you. I think I have something to share, something interesting about Linux. So this is the Linux source code. What else have you expected? This is a hardcore talk. I'm gonna teach you a bit about Linux scheduler, and you have to be careful about this because this knowledge actually applies to every scheduler on every runtime in Java, in .NET, and many others. What does it do? First of all, it has state. This task structure represents your job, represents your thread, represents something that is executable and something that actually tries to talk to a web server, all right? So when you issue a read instruction, a read query, a read system call, it's done by a task struct, all right? An instance of an application. You can call it a thread, you can call it a Go routine, you can call it, I don't know, lightweight thread. What else? Any term would be fine as long as you're comfortable with it. The important thing to understand, and this actually maps and connects to the question that was asked at the beginning of the conversation about the state machine and the state automata theory. This is a state machine because it has state, and the state machine is defined is actually this one, and this state machine is crucial to be understood if you want to be good in I/O and I/O bound stuff, which is practically the entire web, talking to disks, talking to network, talking to sensors somewhere there, and many other remote devices. All of that is I/O because you wait a lot. So this gives you a fundamental state machine that is implemented by practically every runtime. The details, the devil into details, and the implementation, of course, may vary a lot. You have to account for that. But in general, the structure will be like that. And this actually accurately reflects the structure of the modern Linux. It has not been changed for decades already, more than decades. So you start in runnable state, running or runnable. It's abbreviated to the R letter in the tools. If you run a top tool or many other tools, it will be reported shortly as R. This is a common convention used all across the Linux, so you can memorize this stuff. That's going to be useful. Then you either stopped, if you receive a SIG stop, a very simple special signal that asks your program to pause. And then you can continue by issuing a SIG cont. This probably never happens in your live applications. This is kind of supported by the Unix system, but you don't use that. Once your application is exiting, you're becoming a zombie. You're practically waiting for a deallocation. A zombie state says scheduler that it should ignore this task. This task no longer exists and simply was not deallocated. So this is a technical state. You don't need to consider it. You will probably never see processes in a zombie state, hopefully. But these two are important. These two is all about I/O, and these two is where you should be very careful and how you should account for design. You can get either in uninterruptible sleep or interruptible sleep. And that's interesting. What does it even mean? So it means that when you understand that now you're going to perform an operation that will most probably not be instant and will require some time, and during that time there is nothing useful you can do, you can ask your scheduler, you can ask it to put you on sleep. And what that practically means is that the scheduler will take your task structure, will set a correct state here, will set that you fall asleep, will remove you from on CPU and will send this flag to false because you're no longer on off CPU, and will put you in a queue, will put you in a RAM, in a kernel space memory, in a data structure called queue, all right, or run queue or whatever, while you're waiting for an external event. And then kernel will accurately remember what are you waiting for. Why did you decide to sleep? For example, I already showed you the read statement. A lot of them were executed by the Python script, which means kernel is smart enough to figure out that you're trying to read. You fall asleep because you're waiting for the result of that request. And once bytes are received by your network card and go through your IP stack, kernel will notify your task struct. Kernel is smart enough to find it. Kernel will notify your task struct and put you back on CPU. You will jump back on the execution mainline. By the way, here you can see stack. This is exactly the stack you're thinking of. This is the stack of the thread, of the operation system thread. A lot of questions on the interviews, right, about stack and heap. So this is the very essence of the stack. This is where it's born. This is not a kernel level stack. This is a user level stack typically, because task struct typically models user space program, at least in our conversation. But your stack is here. So you will get what's called a context switch, because you've been switched off the CPU and then you hopefully soon enough you got back. This is called context switching. And there are two different strategies, only two. How that can happen? That can happen either voluntarily, when you did it because you understand that this is time to go, and when it happens non-voluntarily, when you actually was kicked off because you're misbehaving. Only two ways of doing that. Most I/O operations like read, like connect, which we have seen already, they do a voluntarily context switch on Linux and many other systems, because this is obviously an operation that will take time, and you don't want to waste your CPU cycles. You don't want to waste your CPU for nothing. Probably there are other jobs that can be done meanwhile, and you want it to be efficiently spread across many task structs in the system. And you have to understand that you can have tens of thousands of that, or even millions, depending upon how much load you have and how much concurrency you have. And kernel scheduler, as well as many schedulers, have 5 different algorithms during their evolution. All the time they come up with a better algorithms that works better for scheduling tasks of different priorities, etc., etc., etc. So counting context switching tells you a lot. And when you see that you have been given a lot of voluntarily context switching, that means that you have been doing a lot of I/O. And that actually indicates that your limiting factor is waiting, not the hardware you have, not the limits of the hardware you have locally on your workstation, but waiting for an external events that do not depend upon you, because the routers in the chain do not depend upon you, because the web server you're talking to does not depend upon you, and you can do nothing about that, and many other factors in the sequence do not depend upon you and your choices, upon your software, chosen algorithm, chosen data structure. None of that matters. And by observing this very proportion, you can be quite sure that you are doing an I/O and you have optimized for waiting. All right, this is how it works. A few numbers tell a lot, and you can be even a bit more. Let me try to show you a eBPF finally. You can be a bit more picky about it. Let's call it like that. Now I'm gonna do complicated stuff. First of all, I need to run this application in the background. It's important. I need to run it into background such that I can later trace it. All right, so now it issues a lot of requests. That's fine. Now let's open another tab, and I will do like this. And I need process ID to be able to trace that particular process. Yeah, we good. I need to type my password correctly. Probably I will not be able to do this from the first try. Not even from the second try. Well, oh, come on. I can't type my password. No, it started. So this is the most glorious and the most modern part of the Linux. I'll spend another 14 minutes explaining to you what's happening right now, and that might be a game changer in your career. If you want to learn something about performance and how to excel at it, how to solve real-world production problems at it live without stopping your system, then be careful. I'm telling you how. Kernel guys, they're smart people, and they created a virtual machine inside kernel. So their reasoning was like that. This system call is expensive. It used to be useful. It's no longer useful because you can't trace live system by them. Tools like perf are also, well, quite reliable. They've been there for decades, but they're heavy. They interfere with the process in the most heavy way. They make it slow. They create excessive load on I/O because they tend to generate a lot of trace files, which can occupy a lot of significant portion of your disk. They will do a lot of writing on the disks, and you can't afford that when your system is under the load. You can't go to production and make it even slower, typically. Well, at least not in the system I've been involved in. You can't do that, and you're starting to have problems that you have tools that cannot be applied to a production. You can only apply it to a local workstation, but representing the same kind of workflow on your extension might be infeasible because you have to reproduce and replicate entire environment, the kind of workflow, real production traffic, etc. Well, that doesn't sound really possible. So that was kind of the rationale behind there. Let's stop it and let's stop this guy. So they invented a virtual machine inside kernel, quite complicated one. And that virtual machine, for example, verifies your eBPF code and rejects any PPF program that has unbound cycles. So if you have a for loop that never terminates and has arbitrarily many cycles, like for while true cycle, for example, then it will be rejected, because that potentially can cause panic in the kernel space, and they are very picky about kernel space. They don't want it to be put in a frozen condition because of the malformed code. So they create a virtual machine, a very special one, which does not give you a general purpose programming language by definition, but it gives you good enough. And it gives you good, and it gives you ability to, I call it interrogate, to interrogate Linux live as it's happening. Any function, any data packet, whatever you have in Linux can be traced live by eBPF because it will be executed in the kernel space. The virtual machine will be is executed alongside with the kernel space. It's part of the kernel space. It gives you access to all the processes, all their states, state of their registers. You can trace everything with that live. And importantly, it does not create an overhead because it runs within the kernel space. It does not run through the system call. It does not talk to the app space. So all this time while I was talking, this program ran in the kernel space. There were no context switching. There were no penalty. Well, almost no penalty, right? Just a few more instructions. It's nothing for the modern system. I got this trace almost for free, all right? And what does it tell me? Well, it gives me a distribution. It gives me a distribution of something I gonna share with you because you have to know about it. It gives me this repo gives you a bunch of scripts well maintained by the community. They are well tested. If you go to tools, I actually compiled it myself to be able to give you the example. If you go to CPU dist, this is exactly the executable I ran. And this is what it tells. This program summarizes tasks on CPU time as a histogram, showing how long tasks spent on the CPU before being descheduled. Once again, you have to understand that this is live and for free without penalty. This provides valuable information that can indicate over subscriptions to many tasks, to few processors, overhead to do excessive context switching, and etc., etc., etc. So it tells you how long you spent on CPU, how long you spent on executing something, and you can actually measure also how long you spent off CPU. Let's do that. Let's run this program again. Let's capture the pit and start it again. Once again, it's happening live. So this program does work, you see, without interruption. But actually, it is interrupted in a certain case because alongside this program, the virtual machine is right now executing the program I loaded, the program maintained by community, this very program. And meanwhile, let's have a look how it works. CPU dist.poo. So it's not written in Python. Python is just the front end. And actually, this is the CPU. This is the BPF code. It looks like C, but it is not exactly C. All right, but it's very similar. And then this stuff is compiled to virtual machine I mentioned, which kernel space understands. And then it's loaded into the kernel space. It's loaded into the kernel space called BPF. Yeah, int open. I don't remember exactly where it is, but it's loaded into the kernel space, and that's why I need sudo. That's why I need super user access. Here we counted on CPU. Now we're gonna count off CPU time. Off CPU time is time we spent waiting for an external event. Well, if I hit Control C right now, then you can compare the histograms, right? You see that we were definitely been waiting for some events. And you see the kind of the segments where we were and how often we hit these segments. That's a true histogram that gives you a lot of understanding. So not only describes you the very essence of the workflow, that like how it's structured, what's the proportion of waiting time to non-waiting time. It also gives you a valuable insight into what are you waiting for and how long. Clearly, you can see two patterns here, for example. So this is one category and this is another. So would you be a guy who implements or tries to optimize this system live? What would you tell your manager? Well, you would tell your manager that you have spotted a potentially promising place where you spend a lot of time. You can see crazy numbers here, where you have account for microseconds, but nonetheless, numbers are crazy comparing to these numbers, for example. And you spot a good place for potential optimization. Now you can start digging and see why are you waiting for such long time, whether you can improve it or not, and many other stuff. And you can do that live. That's crazy. When for a long time that was not production ready. This feature, eBPF stuff, took a long time for kernel developers to be developed firm enough such that it can be used in production system without risk of causing kernel panics. And community eventually came up with repositories like this one, where you can simply download it for free. It's the license gives you opportunity to use it in commercial and non-commercial way as usual, and make the best of it. And by the way, this is the best way to learn how Linux works. This diagram is entirely Linux stack. Everything that runs on Linux is showed here, and every bit of it can be traced by some scripts from this repository, and they are named here: func count, func lower, etc. Unfortunately, we don't have time. We have 5 minutes more. I wanted to to give you more fruitful examples, but I simply don't have time of doing that. The last thing I want to mention is this guy. His name is Brendan Gregg, and he is a famous person in this area. He has a legendary blog. Let me show you. Maybe I can Google it for you. Yeah. A beautiful design. I like it. Well, yeah, it looks ugly, but it's a treasure. Initially at the beginning, this was a blog post, a personal blog post, but eventually he wrote two books that I definitely recommend you to read. They changed a lot in my mindset and taught me a lot how to solve problems, performance problems, and how to analyze things. Read his blog. He writes a lot about perf. He writes a lot about Linux. He writes a lot about eBPF. He is a maintainer and the creator of this repository at the beginning. He was one of the very first guys who created it. And actually, all this stuff was and is consumed live by Netflix, by Facebook, by Google to monitor their live Linux servers 24 hours per 365 days in a year. So they massively adopted it already. And the other industry still not, because people are not aware of that. And finally, as a final remark, you don't have that on Windows or other operation systems, unfortunately. This virtual machine has been implemented only in Linux to the extent I am aware of. I have heard that Windows kind of plans to backport it too, but it will probably take years for obvious reasons. And that kind of limits you or locks you into the Linux. You can't, all these good things which I showed you, while the concepts can be mapped to other platforms, you still have scheduler, you still have on CPU, off CPU, you have context switching, of course, but you can't trace it. You can't trace it because you don't have live access to it. And that's becoming a painful point. And there is a clear distinction between people who know how to make use of Linux and who don't. And one of the distinctions there is using tools. I definitely recommend you, if your life somehow related to Linux, then at least learn how to use these scripts for your benefits. Well, that's it. Thank you. Any questions, any discussions, whatever? Let's have a conversation.
So we have a few questions. Let's maybe go very quickly. So the first question is, I think it's considered the previous question. The main part of my question was trade-off between compiler optimization versus time-to-code optimization. As far as I understand, you recommend to use arrays and simple structures.
Not only I recommend, it's a widely recognized problem. Most of the programming languages, modern programming languages like Go, will claim that they're faster than C or they are competitive with C. How does that work? Well, in the following way. Most of the time when you use C, you use arrays because C does not have standard library with well-defined data structures. You will not implement hash map yourself because you are lazy, because you don't know how, because ad hoc implementation will not be perfect, because you will spend days debugging it and testing it. You don't want that hassle. So what would you do? You would create an array all over the place. Arrays all over the place. That's the ad hoc solution. It's a known phenomena in the industry. In high-level languages, you have data structures, so you would prefer map, or you would take a tree or something better that fits better. So yes, people do that all the time. They use arrays as a base data structure just because they can, because it is there, because it's very easy, and well supported. And that's fine as long as you need CPU intensive implementation. But if you don't, which often you don't need to be CPU efficient all the time. If you don't, then you're in a hard position because your data structure does not fit your problem, and you try to kind of if you have an hammer, you try to nail everything. That's this kind of issue. So I would actually recommend to, first of all, clearly ask yourself whether you need to optimize for CPU in this case, and try to render a clear borderline between CPU optimized code intentionally where it is useful and actually necessary, and the rest of the program when you can go high level and not to bother yourself. That is my recommendation, and I definitely recommend to pick good appropriate data structures from the high-level programming languages and standard libraries. It's a good thing to do. Just always keep in mind that they might not be performing well if you need performance, of course. If you need performance. Next question.
Thank you. Next question. Just a second. Do you think it is better to use loop and arrays versus recursion and trees. And what could be done to optimize work with the trees? What is the role of algorithm in resolving CPU versus I/O bottlenecks problem? eBPF?
Well, eBPF does not relate to the question. Yeah, the question is good. I understand the pain behind it, but you have to, first of all, recall that you can define a tree as an array, all right? If you have never heard that, if that sounds surprising, then Google it. Good luck. You can use array as the base data structure for trees, and there is a simple mathematical rule how you compute a next children index, all right? And you can move back and forth. So you can have a CPU efficient tree, but at the cost of reallocating it all the time. A typical strategy there is to pre-allocate huge array. Well, when I'm saying huge, I mean reasonably huge. Do not occupy your entire memory from the first step, but reasonably huge, and then reuse that array for as much as possible. In this way, avoiding reallocations and this kind of stuff. This is a known technique to solve these problems. Compilers do that a lot. IGEs do that a lot. Well, a lot of other software does that a lot. Well, yeah, that's the technique there. But in general, loops are, of course, much more efficient. And in general, many recursions can be translated to a loop without loss of generality. And many compilers can do that for you. The others can't. It depends upon the compiler. For example, .NET Java can't do that, but Haskell can, for example. Others, probably Scala can. So yeah, it's up to optimizations you have available for you as well. Thanks for the workshop. Very interesting. Do you know about some similar research we can? Yeah, we can talk about scientific novelty for sure. Maybe not now, maybe later. You have my Telegram. Approach me with these questions, please, and we will continue discussion about scientific novelties there. Wonderful workshop, a lot of information to process and digest. Yeah, of course, welcome. Will there be an email or document? Yes, there will be. Basically, just remember eBPF. If you need a starting point, I definitely recommend you this blog. Brendan Gray recommended this name. It's like a Jesus of performance. This guy was hired by Netflix. It was optimizing Netflix. They have like 1,000 of microservices live all the time, and he built a system that traces the entire stack, the entire constellation of the microservices they have live. He built that. He built a lot of scripts. He was one of the guy who was advocating for eBPFs, etc. So he's a very technical person. Every blog post here is a treasure. I can mention that again. So just learn the blog post, and that is a good starting point if you don't know how to start. What about functional programming versus SOAP? Well, nothing about functional programming versus SOAP. This is not the right questions to ask. The fact itself that you're using functional programming or object-oriented programming, it says nothing about how well your code will play with CPU in general. Well, especially not in these days. Previously, memory was an issue, and the functional programmings were avoided because you didn't have enough memory. And there was a kind of a common belief that object-oriented programmings are less memory-intensive. This is no longer true for modern functional programming. Haskell, for example, is quite memory efficient these days and can compete with other platforms for sure. It is not uncommon to find an implementation of a well-recognized algorithm like tree traversal and something like that, graph traversal, that can be compared actually to native C++ implementation in Haskell. And the code itself will be very different. Haskell will do a lot of recursions, a lot of stuff, while C++ obviously will not. Yet they have similar performance nowadays. Well, mainly because functional programming was evolving rapidly for last 25 years. I showed you only one paper that was written 33 years ago. But that was only the beginning, believe me. And there is much more to say. If you want to learn about how these techniques play well with modern infrastructure, then Haskell is the right place to go. A community of Haskell. There are a lot of science people there. I mean, recognized by entire planet at these days. Some of them received Turing Awards, which is the highest possible, how to say, prize or award that then you can get in the field. So learn from them. They publish papers all the time, and which is more important, they often implement their papers. So Haskell continuously evolving. More and more features are introduced into compiler, which are direct translations of the papers previously published. Could you please explain how lambdas and monads are related to performance topics as GPU? Yeah, sure. Async await is a monad. Async await, the very reason why async await eventually was invented in the way we know it right now is because the paper about monad was published, and that paper actually proves that you can be as performant in particular to CPU as all other code, all right? That's important. So if that paper was never been published, and if that proof and that discussion there was not there, then we will probably don't have async await. Start from the point, because these ideas were directly influenced by people who were thinking in terms of monads. Even if you have feeling that these days it is not important, maybe you're right to a certain extent. You don't have a monads explicitly, but the behavior and law and how compiler, sharp compilers, Scala compilers, and other compilers, how they reason about async await and how they rewrite it to make it efficient. That is entirely governed by the kind of monad law in their adoption to the kind of compiler we have. So you can't actually cross it out. You can't. A lot to digest. Yeah, sure. Will be, already answered about the links. Thank you very much for this
Yeah, I think
presentation.
actually, we have many thank you messages, and I don't think we have any other questions.